Zinc-Air battery. Zinc-Air battery is basically a type of battery that is one of the most interesting metal-air batteries. So Zinc-Air battery is obviously a metal-air battery, and so it shares the most important aspect of metal-air battery. So the huge energetic density, the capability to be lighter with respect to other types of devices, storing a lot of energy, but taking advantage of the possibility to take reagent for the development of the reactions from outside the atmosphere, oxygen in this case. So basically, Zinc-Air batteries is a metal-air battery that is composed of one electrode, the anode, that is zinc, and obviously a gas diffusion electrode able to promote diffusions of oxygen at the cathode, at the positive pole, acting as a cathode during the discharging. So if we want to design the structures of a Zinc-Air battery, is the well-known structure. So we have our negative pole that during the discharging is the anode. We have obviously the external circuit, and we have our cathode, the positive pole during discharging, and the electrolyte. So it's important to say that zinc can exist both as primary cell and secondary. That means that for a certain theoretical point of view, these types of battery could be rechargeable, even if there are some limitations concerning, for instance, problem involved in the anode, and even in the cathode, in the electrolyte, but especially in the anode, for what concerns the capability to exploit and develop secondary battery. So it's true that even if Zinc-Air battery has primary batteries, define a mature technology, this is not completely true for what concerns secondary battery, for a lot of different problems that we will see, even if theoretically this could be possible. So we have our, how said, anode during the discharging that is composed of metal, and this metal is zinc. Often, in order to maximize the surface area and so increasing the efficiency, we are using nanoparticles of zinc, particles of zincs in a porous manner. So we are especially thinking to use a binder, basically in order to ensure the contact between these particles. Obviously, we also need to have something that is conductive, but in general we are using a porous substrate on which zinc particles are deposited in order to maximize the interaction, the connection with the electrolyte. So basically we can say that this porous zinc anode, this porous zinc electrode, it should be completely saturated with the electrolyte solution. So here we have the zinc, and the zinc is proceeding with this oxidation. And then on the cathode, we have our well-known oxygen reduction reaction. So we have that zinc 2 plus is created here due to the oxidations of zinc. Electrons are released and collected on this gas diffusion electrode that can take oxygen from outside, and we are able to generate this species and promote the development of the current. This is for what concerns the same reactions involved. If you want to be honest, this product, the generated OH minus, can migrate on the surface of the anode during the discharging, on the surface of the negative electrode, and react together with the zinc 2 plus. And so this means that in reality the real discharging equation, this discharging semi-reaction, is basically this one. We have the zinc that is reacting with 4 times OH minus, and this leads obviously to something that is zinc 2 plus, but it's zinc 2 plus in the form of zincate. So the zincate is this species. So a sort of hydroxide of zinc, in which again we are passing from 0 and 2 plus, so the oxidation is still remain, but is an oxidation in which the zinc released due to this process is interacting with this one, creating the zincate. It is a soluble species. So we are creating the zincate basically on the surface of this electrode. And then we have even an interesting reaction inside the electrolyte. What does it mean? Because often we have focused our attentions only on reaction involving one electrode or the other one. But here we have even another further reaction inside the electrolyte. What does it mean? That when the reaction is proceeding more and more, and so the discharging is proceeding, and the charge level of the battery is decreasing, what is happening is that obviously we are consuming the electrode. More the reaction is proceeding, more zinc is passed from the metallic state to the zincate one. But when the amount of dissolved zinc in the form of zincate is very high, we have an equilibrium between this species and the formation of a zinc oxide plus water plus 2OH minus. So basically what's happened is that when the concentrations of dissolved zinc in the forms of zincate is huge, because the reactions is proceeding by a lot, for instance, we can have the formations of an insoluble species, zinc oxide as a solid. The zincate is soluble, is not a solid, whereas the zinc oxide is a real solid, plus water and this. So this is important in the electrolyte. In lithium, in Zinc-Air battery, we have these types of reaction. And it's important also to describe what is the electrolyte. So in general, the state of art for Zinc-Air battery describes an electrolyte that is an alkaline solution. So we have KOH in an aqueous medium. So in order to ensure a pH value that is around 14. So basically we need to introduce a solution of potassium hydroxide in order to ensure this value of pH. And we will see why this value of pH is crucial. It's crucial because this value of pH allows us to promote the formations of zincate with respect to insoluble hydroxide and inhibit the hydrogen evolution reaction. That is something that is not negligible considering the reduction potentials of the zinc reaction. What does it mean? So it's in order to understand these concepts and why it's so important to work in super alkaline condition, it's important to remember the poor bed diagram of zinc and look at what types of side reaction involving the corrosions of the electrons can be present. But before doing this, it's important to say that for what concerns Zinc-Air battery, these types of device is so interesting because it's a metal air battery, and so we are sharing each single types of characteristics. We are sharing the high energetic density, we are sharing the high powers, the high specific power, and but the zinc is basically something that is really cheap, really abundant, is the 24th most abundant element in Earth, basically. And it's also extremely important to remember another aspect, that the reduction potentials of this reaction in this pH condition, because we need to remember that sometimes, obviously not always, but sometimes the presence of the pH, a different pH can change in according with the Nernst equation, the reduction potential. So in this situation we can say that the reduction potential of the zinc is equal to minus 1.25, and the one of oxygen reaction is plus 0.4, minus 1.25 volt plus 0.5 volts. So the difference is the DDP, and is equal to 1.65 volt. Obviously, this is only the theoretical one. The one calculated concerning the potential that are reducing potential, the potentials of the nearest equation. But we know that the potentials of the nearest equation are basically potentials in an open circuit condition, and so we are not considering the overtension. If we have some concern about the overtension, we can take in consider this aspect, that some energy is lost, because the energy consumption, the energy basically that we can discharge on the resistance is decreased. The useful work is decreased if we are running a current. We have well described these topics speaking about both thermodynamics and cynetics in electrochemistry. And so what does it mean is that we are not able to take advantage of this overall DDP, but the actual real DDP, it will be smaller, and it will be between 1.35 and 1.4. But it's quite interesting voltage, significantly higher with respect, for instance, a fuel cell, but even significantly smaller with respect a lithium-ion battery. But what is interesting about the metal-air battery as the zinc with respect to the lithium one is the price, since the cost is reduced, and is also the energetic density. So now it's important to remember that Zinc-Air battery, house said, can be present in the market mainly as primary battery. Why? Because we have some problem due to the rechargeabilities, the capability to develop a secondary battery. And from a theoretical point of view, the zinc is good for create secondary battery, because even if the Pourbet diagram seems to tell us something else, from a cinetic point of view, it's possible in a quite easily way to promote the redeposition of zinc 2+ as metallic zinc in water. So the redepositions of zinc from zinc 2+ to metallic zinc in water is something that could be done very well. Let's imagine the creations of a film of zinc, for instance, on metal substrate in order to protect this metal substrate versus the corrosion. It's a quite mature technology. So we know that zinc is a really active metal for a possible redepositions in water. And so what does it mean? That from a theoretical point of view, is since we are in a water system, and since we have zinc 2+, and since we need to regenerate metallic zinc from a theoretical point of view, by applying an external voltage, it's possible to imagine to regenerate the starting situation. It's something that from a theoretical point of view works. But in the reality, we need to face up with different problems, especially involving the anode. Anode, how we said, is composed of zinc, metallic zinc, or a powder of zinc, in order to maximize in a porous anode the interaction with electrolyte that is saturated with electrolyte, basically. So now it's important to describe which types of problems are present on the anode and on the cathode and on the electrolyte, limiting the possibility to use zinc-8 battery as secondary battery. The first problem is obviously the fact that we have defined, so the first problem, problems for the development of secondary Zinc-Air battery. The problems for the development of these batteries are different. So we have, for instance, the first problem lies in what we have described speaking about the reaction present in the electrolyte. So the equilibrium between the zincate and the zinc oxide, plus water, plus 2 times OH-. What does it mean? That when we are increasing more and more the discharging, when we are approaching a high level of discharging, we are increasing the dissolution of zinc and zincate 2-. And this literally means that we are shifting a little bit the equilibrium toward the formations of zinc oxide, this species. But when we are forming a zinc oxide, this is a solid, this is an insoluble species. And if we want to redesign here our cell, if our reaction is proceeding more and more, we are more and more producing zinc 2 plus that is reacting with the release of H minus in order to form Zinc-8. So we are creating a lot of Zinc-8 basically here on the surface. But when this Zinc-8 is too much, this equilibrium can be shifted in this direction and we can appreciate the formation of an oxide. But this oxide is a solid that can be deposited here on the surface of the electron. And what does it mean? That we are acting with this zinc oxide that is behaving as a sort of real physical barrier due to the diffusion of OH minus that are not able to diffuse anymore since we have this physical barrier of zinc oxide. And this means that the circuit is simply closed and the final DDP is decreased and the total efficiency is decreased. So this is one of the most important anodic problems, the generations of something that is so insoluble and stable and can act as a sort of something that can close the circuit. So this is the first problem that is known as passivation, since we are creating a zinc oxide on a metallic zinc. So a well-known, for instance, phenomenon in corrosion science. And so this is the passivation. The first problem is the passivation of the anode, obviously, the negative pole, since we are speaking about discharging now. So then we have a second problem, and the second problem arises in the reduction of zinc 2 plus in metallic zinc. So during the charging process, for instance, what we are doing is apply a potential difference in order to increase the potential of this species with respect to this one. And so, if spontaneously the movement of electron is this one during charging process, we are forcing the different types of pathway. And so the electrons are moving in this way, and the zinc 2 plus existence in Zinc-8 can react with these electrons in order to recollect it as metallic zinc. And this can be done. This works. It's what we do, for instance, for zinc metal depositions for protections of materials from corrosion. This works. But what is the problem is that if we have a huge amount of zinc 2 plus dissolved here, as present at Zinc-8 obviously, but let's draw this at zinc 2 plus. We have 1, 2, 3 and so on. So we have a lot of different zinc 2 plus present in Zinc-8. When we are forcing the reduction in order to recreate metallic zinc, the problem is that since we have a huge amount, we can generate aggregate. So basically these types of zinc 2 plus can react in sort of blocks of metallic zinc. And in general, the repositions is not uniform, because at the very beginning we have a very uniform zinc electrode, because we have designed it in the industry, basically, in a company with specific machine in order to homogenize the surface, and is basically created in a firm. Whereas when we are regenerating the zinc due to the applying of a potential, it's not so obvious that the repositions is completely homogeneous in each point. And so maybe at the very beginning we can have a plate and homogeneous surface, but later when we want to regenerate the substrate, maybe some zinc 2 plus prefer arrive here, a little bit less here, maybe a little bit more here, and we are basically losing the homogeneous shape and the smooth shape of before. We are creating a change in morphology, and this is a problem for the performance of the battery, because since we are modifying and decreasing the homogeneity of the electrode, the DDP decrease and the final performance decrease when we are running a further discharging process later. And another extremely important process is that remembering that we have a membrane, a permeable, ionic impermeable membrane in order to close the circuit, avoiding the contact between the electrode. if the reposition mechanism is so bad and so localized in one point in order to create something that can break down this membrane and even maybe reach the other electrode, we can cause a short-circuit and make the system to explode. And so basically this is a really problem, this is a really hazard also. So the second problem lies in bad redeposition mechanisms with the formations of aggregate and changing the morphology. So the redeposition mechanisms. And then we have even another problem concerning the anode, but these two are probably the most difficult to be solved problems. These can be mitigated by avoiding to discharge completely the battery, but this is something that is always present. Then we have the third problem is the corrosion of electrode. What does it mean? So what is corrosion? Basically the corrosion is a sort of electrochemical process because involve two redox couple, involve an oxidation, that is the species that is corroding, and a reduction, that is the species that allow to ensure the corrosion. So basically the corrosion is a sort of short-circuited battery. And in this case the corrosion is to do the fact that if we remember the Purbe diagram of zinc, pH versus open circuit potential, these are the line of water. So this is 0 and this is 1.3. This is the existing zone of water, this is oxygen, and this is hydrogen. This line corresponds to the line of hydrogen reduction, and this line corresponds to the line of oxygen reduction. We know that the zinc is basically equal to minus 1.25, and so it is here. And we have a Purbe diagram of zinc that is something like this. Here we have the formation of a solid oxide, and here we have the Zinc-Air, the formation of a soluble oxide when we are approaching pH higher than 14, around 14, obviously 14 is the maximum, but close to 14. 14. So what basically the Purbe diagram of zinc tells us? That if this is the line of zinc reduction, we are looking at a diagram in which here we have zinc as metallic zinc, here we have zinc as zinc 2+, and the corresponding oxide when we are approaching higher pH, and so protonic reaction as what we have described speaking about Purbe diagram in the dedicating lesson. So what is important here is that when we are in this condition, so the electrode is actually working at this potential, and we are in an electrolytic zone with an electrolyte that is water-based. We are in a situation in which zinc is in water. But we know that metallic zinc is not stable in water, because zinc is stable in zinc 2+ in water. And so what is happening is that we know that the reaction, in this case, the working principle of Zinc-Air battery, involve the reduction of the oxidations of zinc and the reductions of oxygen. But here we have even another possible reaction that is present. We have the hydrogen. And so what is a possibility is that the zinc oxidation can start and can ensure not the reduction of oxygen, but can promote the reduction of hydrogen. What does it mean? If let me cancel for a while the two main important problems. If we have, for instance, our cell in the moment in which we are promoting the reaction, zinc passes from the metallic state to zinc 2+ in the Zinc-Air. and electrons are collected here. And these electrons can promote the reduction of oxygen that can release OH- that can react with this one and create zincate. And so the circuit is closed and we are actually discharging electron on the resistance. But what's happened is that according with the Purbe diagram, since we are working on an electrolyte that contains water, so we have an aqueous medium, we are also in this potential condition, minus 1.25, the possibility to have this reaction. So what does it mean? That the water can be reduced in order to form hydrogen. And what is the problem in this case? That if the reduced component is not oxygen, but is water in order to form hydrogen, this means that these electrons are not collected here, because we have the oxidations of the zinc, but these electrons are directly given to water in order to produce hydrogen. And so these electrons are not collected in the external circuit, because basically hydrogen is directly in contact with zinc. We do not need to pass from an external circuit. Water is directly in contact, since water is one of the main components of the electrolyte. And so we have the generations of hydrogen as a product of this reduction leading to the oxidations of zinc. And so zinc is oxidized, as in the case of this reaction. But in this case, this oxidation consumes zinc. But with a consumption of zinc, hydrogens are produced. And so the current can flow, because these electrons are produced. And these electrons can follow this pathway and be discharged on the resistance. But in these reactions, electrons are not collected here, and so zinc is just simply consumed, but not in a useful way, because it's oxidized. Yes, it's good, but it's oxidized with a reduction of something that is not on the other electrode. It's basically a corrosion reaction, because this oxidation don't involve the generation of useful work, because no electrons are flowing in the external circuit. And this is why we are speaking about corrosion of electrode, because the oxidation starts, but is not starting in a useful way. So we are just simply lost matter. We are simply lost zinc, because we are creating, yes, zinc 2+, but in a useless way, because we are reducing not oxygen, but hydrogen. And so what is happening is that we can have a side reaction that involve the oxidations of zinc reacting with 2OH-, creating this product. But these oxidations of zinc, again from 0 and 2+, involve this reaction. The evolution of hydrogen due to the reductions of water, and so no exchange of electrons. Obviously exchange of electrons is present, but these electrons are not passing through the external circuit, and so we are not creating a useful current. And in which way we can fight this problem? If we look at the Purbe diagram, it's quite interesting to observe that in the case in which the oxidation is proceeding due to the formation of zincate, this means that we are promoting the reductions of oxygen. When the zinc oxidation is proceeding toward the formations of these different types of hydroxide, this means that we are promoting the reductions of water in order to create hydrogen. And so we want to promote these reactions, fighting these side reactions. And what we can do, look at the Purbe diagram, we can work in superalkaline condition, when the pH is close around 14. Because in this condition, we are promoting the existence of the zincate, but the existence of a zincate means, in order to exist, that we are promoting these types of reaction with respect to this one. And so work in these conditions, we respect this one, so in super alkaline condition, means that from a synetical point of view, we are inhibiting the hydrogen evolution reactions and promoting the oxygen reduction reaction. And so we need to work in super alkaline condition in order to avoid this side effect connected with the formation of hydrogen and the corrosion of the electron.